Hey guys, so in this video we're going to look at a circuit where we have a sinusoidal source and we want to figure out with this input sinusoid what our output over this capacitor here looks like. And so it turns out the process for looking at sinusoidal sources versus DC sources is very similar. We just have to know how to deal with these sinusoid sources correctly, and it actually poses a fun and challenging problem. So what's the first thing we do whenever we're working with circuits? Well, we look to see if there's any frequency-dependent components. And as you can see here, since we have this capacitor, we do have frequency-dependent components, so we need to convert over to the complex impedance domain. So I'm going to redraw this circuit with complex impedance boxes in it. So we know the sources are going to stay the same. And resistors are not frequency-dependent, so its complex impedance is just 1 still. But capacitors are frequency dependent. So if you guys remember from previous videos, the impedance of a capacitor goes down as frequency increases. So that's why we have the formula 1 over C J 2 pi F. And I'm going to simplify that down to be just 1 over JF. Okay, awesome. So, oops, sorry, I pressed the wrong key there. We've converted over to the complex impedance domain. So what's the next thing we do? Well, we want to figure out an input-output relationship, so we better figure out what the transfer function is. And the transfer function is pretty simple, right? Because we just have two components in series, and so that's just a simple formula, and so I'm going to write that down. H of F is equal to 1 over JF all over 1 plus 1 all over JF. And of course we can simplify that down to be 1 over JF plus 1. Okay, awesome. Found our transfer function. So now we have to figure out how to deal with this sinusoid. And this is where I think Dr. Johnson doesn't do as great of a job as he possibly could, because he doesn't give you a very mathematically rigorous definition of how to deal with these things. You will get a mathematically rigorous definition when you go into 242. So what I'm going to try and do here is bridge between the two, so maybe you get a little bit of a better understanding. And so how do we deal with this? We have to write our sinusoid in a different way. And the easiest thing we can do is write it as a sum of complex exponentials. So we know the 10 is going to stay there. But how do we write sine? This should just be one of the formulas you have memorized and on your cheat sheet for exams. So it's e to the j theta, and theta here is equal to 2 pi t, minus e to the negative j theta, all over 2j. Okay. So here's the central lesson of dealing with sinusoids. You convert to complex exponential form, and then you input each complex exponential separately into the circuit. And why do you input a complex exponential into the circuit? And well, that's because for every LTI system, inserting a complex exponential spits out a complex exponential. And furthermore, the frequency must stay the same for that complex exponential. So here, it's going to stay the same. The only differences could be you might have a new magnitude, or you might have a phase change. So we might be adding to the complex exponential. But that makes our job a lot easier, right? Because we know this frequency is going to stay the same. We know we're going to get a complex exponential out. There's just going to be slight modifications, like an addition or a multiplication out here. So let's go ahead and do that. Let's insert each complex exponential into the system. So I'm going to insert this complex exponential first. I'm going to ignore the constants, 10 over 2j on the outside, because we can multiply by those later and it doesn't make a difference. So e to the j 2 pi t. What's the frequency of this? Well, frequency is hidden, but we know it's equal to 1, right? It's just implied because frequency is j 2 pi ft, right? And so we're going to insert that in to here. So then we get h of 1 is equal to 1 over j plus 1. All right, now I'm going to insert the other complex exponential in. And once again, I'm going to ignore the constants on the outside. E to the j 2 pi negative 1 t. So we're inserting our frequency of negative 1 you're going to get 1 over minus j plus 1. Awesome. And I'm just going to simplify these really quickly. So I don't really like to deal with j's in the denominator. It's much easier to multiply by the conjugate and get them on the top. So this is equal to 1 minus j over 2. And this is equal to 1 plus j over 2. And you can just figure that out by multiplying by the conjugate. Okay, so these are the scaling factors that help indicate the magnitude and phase changes to these complex exponentials. So all we have to do is take these values and multiply them next to their respective complex exponentials, and we have our final answer. So really all we need to do is we need to take this formula, so I'm going to expand it out a little bit. So we have the 10 over 2j, just taking the constants here. And for the first complex exponential, we had this value, so the 1 minus j over 2. And multiply by the complex exponential. And we're going to add that to the other part up here. So we have constants again, and I'm not forgetting the minus sign. We multiply by the scaling factor, which helps tell you how that complex exponential changed in magnitude and phase, but again, not in frequency, and the complex exponential. Okay, so this technically is the solution to the output, but this isn't a real valued signal, right? We have a bunch of j's in it, and for all the problems you're going to be dealing with in ELEC 241, you should be able to simplify them back down to regular old sines and cosines. So let's try and work with this a little bit better so we can get a nicer solution. So I'm going to go ahead and multiply these two parts together. So we get 10 minus 10j all over 4j times our complex exponential. And we can make that a little bit nicer looking. So I'm going to say that's 5 all over 2 times 2j. And you're going to see why I wrote it like that a little bit later. Plus minus 5 over 2 times the complex exponential. Plus minus 10 minus 10j all over 2 times 2j times the other complex exponential. And it's at this point where you should be able to see that we still have our original sines and cosines, right? You should be able to see that there's 2j's on the bottom and complex exponentials of different signs. So that immediately tells you that we have a sine function here. Then you should also see that since we have 2's on the bottom and then complex exponentials of the same sign, that we have a cosine here. So let's try and separate this out a little bit better. So I'm going to separate it out. Oh, here, let's do this a little bit better. See, I did this one this way where I actually separated it out. I did not do that one this way, so let's just go ahead and erase that and make it all look the same just to make our lives easier. The eraser function is not very good on this tablet. You kind of have to like scratch in order to get it to work. So let's do that one more time. So it should be minus 5 over 2 times 2j minus 5 all over 4. Oops, there was a mistake there, 5 over 4. Oh no, it's 5 over 2, right? Sorry, it's late here and I haven't done this problem before. I'm just kind of making it up and seeing how it goes. Okay, does that look right to all you guys? 10 minus 10j over 4j, we separate that out, so it should be 10 over 2 times 2j minus 5 over 2, and then we have minus 10 minus 10j over 4j, so that should turn into minus 5 minus... Wow, I'm doing so bad here tonight. Okay. There we go. This looks better now. All 2's on the bottom. There should be no 4's in the denominator once I simplified down that 10. Okay, here we go. So that looks better. Okay. So you can still see here that we have 2 j's on the bottom, which helps indicate sine. And then we have 2's on the bottom, which helps indicate cosine. So let's separate out the sine components first. So pulling out the sine components, we get 5 over 2j times e to the j 2 pi t minus 5 over 2j minus j 2 pi t. All right, so this is going to turn into our sine, and then let's separate out the cosine components. Minus 5 over 2 e to the j 2 pi t, and minus 5 over 2 e to the minus j 2 pi t. Okay, so what does this one look like? Well, this looks like 5 sine 2 pi t. And this looks like minus 5 cosine 2 pi t. And so we sum them up, and that's the final answer. So our final answer should be 5 sine 2 pi t plus negative 5 cosine 2 pi t. And do check me on my work, you guys. The general process here is correct, but it's highly likely I made some algebra errors. So just take a look back at what I did and learn the process. Maybe not pay as much attention to the algebra. But yeah, hope this video helped, and I'll see you guys in the next one.